Hello and welcome to another Coding Geeks. We are Gizmo and
X
and
Deja vu.
we are all geeks from Michelle. Deja vu is my little brother, but I won't tell you. Today we learn a bit cracking basics. So for this, we use the x64 debug application. It's a debugger for Windows, and we will crack an executable named Amaze Me, which you need to download now.
Okay, where can I find it?
You can find it on WeChalNet.
Do I have to register or log in?
No, downloads.
Amaze Me.
Amaze Me.
And
So,
I suppose I need to run it.
the first thing you do when you analyze an executable, the first thing you usually do is start it, but it can be dangerous if you analyze malware. You should, of course, not simply start it, but this is a clean application you can debug with x64 debug. You can run the application in the normal way first. The application is a simple window with a text box and a button.
And it doesn't like if I just click check.
Exactly, and it's supposed that you write the solution there, check it, and it says congratulations. Okay, you maybe enter some text and click check again. You will get a no again.
Okay.
Yeah, close the application.
And here it is opened in x64 debug.
Exactly. So let me explain you the application a bit, the Xdebug. You have 4 windows. The upper left is the disassembly, where you see assembler code. Yes, you see on the most left, you see the address of the process. 77
address.
Exactly. This is the address in memory.
Okay.
And in the middle, you have the machine code opcodes. This is the actual program in hex. For example, you see the opcode CC is int3. It's assembly opcode.
Or this one here. Yeah.
Or maybe 8BFF is a morph from 80 to 80. On the right, you see the assembler mnemonics, as it's called. It's the assembly. This is the assembly representation of the opcodes.
Okay, what does opcodes mean?
The CC is the opcode, the machine code, the operation code.
Okay.
Opcode. CC is the opcode, and int3 is the assembly mnemonic. It's a bit easier to read assembly than just numeric opcodes. And for example, if you look at the 6A16, the push 16 a bit below, 6A is the opcode for push, and 16 is a parameter. 6A expect 1 byte as parameter. It's pushing 16 on the stack, but we come to this later. Okay, so left we have assembly view, disassembly. On the right, you see the CPU registers.
This one here.
Yes, you see the EAX. This is the A register. It holds the value 0 at the moment, and this is the register in your CPU.
Okay.
And this CPU has several registers. The A, EAX, EBX, ECX, EDX are general purpose registers, and the A, you can say it's an accumulator register. It's used for mathematical operations. If you add 2 numbers, the result will be an EAX. But they are general purpose register. You can use it for different purposes, but its main purpose is as accumulator and to transfer parameters to functions and as return value from functions. So the EAX register is used heavily. EBX is just the same as the second register. It's also general purpose. ECX is also general purpose. It's often used as counter register. You can remember C for counter register. It's used in loops to store the value of your loop position. But it's also general purpose. It's just a convention. You don't have to use it this way, but you can. And EDX is often used for data pointers. It often holds a pointer to some data. A pointer is just a memory address.
It points to a specific address.
Yes. Then EBP and ESP is a bit different. Those is a stack base pointer. EBP is a base pointer for the stack, and ESP is a stack pointer, the top of the stack. And maybe let's jump to the lower right window. This is the stack.
This one.
This is the stack. Yes, you have the memory address on the left. And In the middle, you have the value of the stack.
Mm-hmm.
And on the right, you have some help from Xdebug, what this could mean. It must not be correct, but it could mean. For example, the Amaze Me exe string, the 5D, this is just maybe a pointer to a segment in the exe. I'm not sure. 5D has no special meaning to me. And on the lower left, you have a few for general memory. So you can analyze a hex dump of any memory address there.
Mm-hmm.
Okay, so ESP, EBP are for the stack. The base pointer is the current stack frame, the begin, and the ESP is the top of the stack for the current frame. We will see how this works soon. And
So
then
if
you
I'm
have
gonna scroll to the top here, no. I
what's
thought
maybe
that the number should apply to this one here.
yeah, correctly. This is a stack pointer, yeah.
Okay.
And then we have more registers, ESI and EDI. ESI is a stack segment index. Not sure. It's a pointer for various assembly functions. It's a pointer to the start of a memory somewhere. You can do assembly commands that use ESI or EDI as a base and add an offset. That's what those two registers are for. And now the most important register maybe is the EIP. It's the instruction pointer.
Okay.
And in this register, this is the memory address where the CPU is at the very moment.
Okay.
If you look at the value 77B778E8, this is exactly there on the green dot.
Here.
Yeah, and this is exactly where the CPU is at the very moment. So if you execute this instruction, the EB07, it's a jump to a pointer. It's a short jump, 7 bytes away, and maybe execute this instruction.
Okay, in this line is this the path
Where it
the
will go,
instruction
yes.
pointer will take. Okay. This one?
Yeah. German step into is it's in English. And you see it jumped right there.
Mm-hmm.
And the next instruction would be a C745. And this is a move. And the parameters this move takes is maybe an offset and a memory address. FC is -4. You see, this move is also using the SS stack segment. It's using the ESI as base, subtracts 4, and then moves the value FFF into it. Maybe just step over or step into this. Execute this instruction. Pum, pum, pum. What happened?
It stepped one down below.
Yeah, it moved something to the stack, maybe, not sure. Okay, maybe do the next instruction. It will make more sense soon. You see the ECX is now red.
Mm-hmm.
So this means this value changed and it moved, and the previous instruction moved from the stack base pointer -10 into the ECX. So it moved a value to the ECX register. So before we really get started, the memory where we are executing at the moment, 77B7, this is from NTDLL. It's Windows internals. It's not user code. It's not the code from Amaze Me.exe.
Mm-hmm.
To get to the start of the program into the main function, we need to disable a breakpoint. Go to settings. Yes. System breakpoint. Disable the system breakpoint.
This one. Okay.
Okay. Save. And reload the application again. It's Amaze Me is a very old crackit from TBS back in the days, but it's perfect to learn assembly and a bit debugger stuff. Okay, now we are at a different memory address. We are now at 41,000.
Mm-hmm.
And this is the main entry point of your application. If you write a program in main, there is the start. It's there. It's by convention. It starts by 40,000. This is the memory address of the user space.
And the reason why we are here now is because we changed the breakpoint. Yes.
Yeah, exactly. This is now the main breakpoint.
Okay.
And before we were in the loading process, if you have applications with mean anti-debugging tricks, you probably need a breakpoint in the system first. But in this application, you can directly jump to the user code. If we execute this instruction, it is a push 11. Push is pushing a value on the stack, and the 11 is probably hex or decimal, not sure. I think it's decimal. It pushes 11 on the stack. Executes this. Oh no, it's hex. And you see the stack changed. It now pushed an 11 on the stack. At the very top of the stack.
Ah, there, here. Yes. Okay.
Yeah. So this is what the instruction did. It pushed an 11 on the stack, and when you push something on the stack with a push mnemonic, the ESP also changes. So the top of the stack also got -4, and now the stack knows, my end is there at the top. If you do a push, it changes the stack pointer. And if you do a pop, it changes the stack pointer back again by 4 bytes. And this brings us to function calling. The next instruction is a call, and it takes as parameter a memory address where the function is changing the EIP, the instruction pointer, to the value. And by this, it's calling the function. And maybe step into. Now we jumped there. You see the EIP changed. And also the stack pointer changed. If you do a call, it is taking the base pointer, puts it to the stack pointer, and decrease or grow the stack by, no, it does not grow the stack. You have to do that manually, but it's pushing the base pointer on the stack. And by this, it knows where it is coming from. And if you return from a call, it is just doing it in reverse, taking the old instruction pointer from the stack and puts it back to EIP. Does it make sense?
Yeah, I think so.
So this is how calling works on x64. You push the old base pointer on the stack. The EIP is on the stack. You see 40,1007. This is the old EIP. And by this, it knows how to return where it come from. Now we are at 4012cc. And this instruction is a jump somewhere to kernel space. This is a Windows function, get stock object. It's getting an icon. And you see the 11 on the stack?
Yeah, here.
This is a parameter for the function. It wants icon hex 11, which is some Windows icon. Now, if you follow this jump, you will go into kernel, but do it.
Hit
Execute.
this button here?
Yeah.
Okay.
Now we are somewhere in Windows kernel. Move EDI does nothing, I think. Step over.
This here?
Yeah. Yeah, it did nothing. EDI did not change. So now if you have a function and a function wants to use stack, you have to push the base pointer on the stack. Now it's pushing the base pointer on the stack. You can do this.
One step or step into?
Doesn't matter. Step over and step into is only interesting if you have a call instruction. If you have a call instruction, say step over, it executes the whole call. And if you say step into, you follow the code.
Okay. If I were here, for example, it would jump to this one here, and then if I hit step over, this would be this one. If I understand correctly.
No, wrong. Maybe let us follow the code. At next, we push the base pointer on the stack. Do it. You see, now it's the base pointer on the stack. Then it moves the stack pointer to the base pointer, changing the current stack frame this way, execute. And now you see in the stack the red line from return to amaze me down to 19 FFDC. The red line in the stack.
Yeah.
Near stack frame lower right is the red line at the memory addresses. The clamps, the cramps. Yes, yes. And this is the stack frame. It goes from the stack pointer to the base pointer.
Yeah.
And by this, if you call functions, you create frames of stack frame by frame by frame. For every call, you create a frame this way. And this is how function calling works in computers. So it remembers where's the old base pointer, changes the base pointer to the current stack pointer, and then maybe pushing more on the stack or not.
Mm-hmm.
But you see the red line indicates the stack frame.
Okay.
Okay, execute the next two and until the call.
Until the call here.
Yeah. And now you can choose between step over or step into. If you step into, you follow the call. If you step over, you only execute it. You know, when you do the call, it executes the instructions at the call address. And then it returns, it will land here again. And if you step over, you do all the code, but you do not follow in debugger.
Okay. I won't see what's especially done within the call.
Correct.
Okay.
Yeah, step over. This is GDI, it's Windows graphics library. Test EAX it's comparing EAX with EAX and maybe set the carry flag or something. Maybe execute it. Execute the test. Did something change? E-flags may be changed. No idea what this is. So we did not talk about flags yet.
It's flags, this one here, or what do you mean?
Yeah, those flags, exactly. ZF, if you hover over it, it's a 0 flag. Is set if the result is 0. And the test now checked EAX, which is value null, checks null against null, and sets the 0 flag. It does not indicate red because 0 flag was 1 before. But if it have been 0, it would set it to 1 now. And the flag is like a register, but only 1 bit.
Yeah.
What is OF?
Overflow
flag.
So those flags are only for indicating something to.
Yeah, it's like a CPU state.
Okay.
Then carry flag overflow is set if you add 2 large numbers and the result does not fit in 32 bits or 64 bits. It will overflow. It will start by 0 again, and then it sets the carry flag. So you know, oh, it was an overflow. I have to handle this case.
Okay.
Yeah. Okay. So the previous instruction was a test. It sets the 0 flag. And if jump equal will jump if the 0 flag is set. You can see jump is taken below the assembly. And you see it also by the red line. It will jump equal because the 0 flag is set. Yeah, maybe follow the. Now it does not matter if you step into or step over. It's only for calls.
Okay.
Now you can decide again if you jump over, jump in. I would say step over. Maybe click on the red 4. Right click on the red 4 at the bottom.
Red
a bit
4.
Below.
Red. You mean red by red, not color.
Yeah.
So
please do a right click on the red. Trace coverage. No, I thought we can maybe set EIP here is interesting. But do not do it. It will change the program behavior. And with this nice x64 debug, you can also change the flags on the fly, or change register values, or change memory. You can manipulate the program flow, but we should not.
And in this case, it would set the instruction pointer to here, or what?
Yeah.
Okay.
Which will effectively cancel out all the previous instructions. But let's just follow the code, step into or step over. Testing AL now. AL is EAX, but only the lower 8 bits. It's the low byte of the A register, AL, or A low. And in 64 mode, the registers are called RAX with an R in the beginning. So you know if it's 64 bits or if you only take 32 bits. Then you can do 16 bits and 8 bits. Follow the code more. I want to go to a return. Now the return does a pop from the stack. It will pop the address of the Amaze Me 41007, put it in the EIP, and by this we return to where we come from, into our user land.
Okay.
So follow. And now we are back. Scroll a bit up. So you see we did the call, and now we are back where we come from. So the next instruction is moving the EAX into a data segment pointer. Maybe right click on this instruction, follow in dump, constant Amaze Me. If you do selected address, you can do this maybe for a show. Follow in dump, selected address. Now you are at the 1007. This is the machine code. This is the same as the middle bar. You see the A374.
Yeah.
This is the raw machine code. And now you follow your machine code in the dump, but we do not want this. I just wanted to show you.
Okay. So I do it, where is it? Like this again.
Yeah. And this is a bit higher address. It's some data segment in the executable. An executable can have data and code segments and a bit more, but the code is the machine code, and the data segments are some strings maybe, or constants. Okay, now if you execute this instruction, you see the dump changed. It was 000 before, and now you have.
See anything.
You didn't see anything?
No, I don't.
It has written the EAX value into this memory address, into the 40374. It wrote the value of EAX.
Okay.
You can compare the value of EAX, and the first 4 bytes in the memory dump are the same now. What's maybe interesting is that the CPU registers are maybe little endian and the memory is big endian, or the other way around. That's because the values are turned around. You have 04 BA, and in the dump you have BA 04. 8A. Okay, so it has written the EAX into some memory. Next it does, it's pushing a 0 on the stack. You can execute this. You see the stack pointer changed and the stack changed. There's the 0 on the top of the stack now. The stack pointer got decreased by 4. Now it's calling a Windows function again. Get module handle is getting the window of the program, the main window. I think EAX as the value of 0 as parameter is probably meaning it's returning the main window. We step over, we don't care. Then it's moving EAX. In EAX, we have the return value of the function. It's plain 40,000 and it's pushing the 40,000 on in the memory again. And exactly 4 bytes below, you can follow and dump again. Constant again. Now you see all 0 at in the memory dump in the interesting first 4 bytes. And now it's writing the value of EAX there again. You can execute this, and then you should have. You see it changed the green line here. Yeah. So this is what this opcode did. Now next it's pushing 3 values again on the stack, pushing a pointer on the stack. Then it calls an Amaze Me function. It's a function from the user code, and maybe we should follow this. Step into. So and you can tell it just jumped 4 bytes. It called 4 bytes of 8 bytes away. When we return from this function, it will call exit process. You understand this? If we return from this call, we land back on the push EAX and then exit process. So this must be some main method.
Okay. There's the exit process. Okay. Now I understand. Yes. Shall I run it or?
Yeah, run a bit farther. Now it's a call. It's pushing the base pointer again. Then it registers a new stack frame. Then it subtracts something from the stack pointer to enlarge it. Creating a new stack frame. Maybe do this. Now, if you do the add ESP, you have a new stack frame. If you do this now, you see it, stack totally changed.
Here, or what do you mean?
Yeah, and also the stack in the stack frame at the bottom right. Scroll a bit down, maybe. A bit up. There's this. I think we are now at FF10. Oh no, we are more up. There.
Yeah.
Okay. Let's continue. Now it's pushing more values on the stack, but relative to the base pointer, filling the stack frame with function parameters. Execute a few moves. You see now the stack changes there. Pushing more. Popping something, okay. Pushing a 10. Pushing a 0. Pushing a pointer to our memory. The 43,000 is some memory of the application.
This one here, I believe.
Yeah, and it starts with a string. And the Xdebug also says, oh, this is a string Amaze Me by BB.
Yeah.
Let's execute more. So now if you have a new application, you have first look around a bit, try a bit things out, look how it works.
Here's the no that gets displayed when I enter the wrong information, I believe.
Yeah.
Is that correct?
Yeah, correct.
And here would be displayed if I'm amazed. As if I entered the correct information, I would end here, or this would would have been read from the stack or whatever.
Yeah. But first now it's still setting up stuff. It's first creating a window, loading an icon, display, set the title.
Okay.
Then it will need to register some handler for the events. We will come to this very soon. Let's execute some more. Step over. Then it calls load icon. It's loading the icon from the stock object. We step over, uninteresting. Moving some EAX on the stack, some zeros, another zero on the stack. Then a constant 7F is pushed on the stack. A zero is pushed on the stack. Then it loads the cursor. It's also Windows function, uninteresting.
What does the LEA mean?
Load effective address.
Okay.
It is loading the pointer into EAX. It's loading a pointer into EAX. A pointer on the stack. Stack base pointer -30 is hex 30 bytes up from the base pointer. So in our current stack frame, 0x 30 bytes up. What did it load? 19FF into EAX. Pushing EAX. Register class. I have no idea what this really does. It probably registers the window into the event handler, maybe, not sure. But it's not really important. Oh no, it cannot be the window. The create window is coming up next. Now it's pushing the parameters for create window.
So I can step over them, I believe.
Yeah. Step over, create window. Then it's pushing the window address on the stack, pushing a 1.
And show window
Push.
function. Is this function displays the window on the screen, or?
Yeah, I think so. If you execute this, it should show the window. You see?
Yeah. It's still loading because the code itself is still running.
Yeah, correct.
Okay. Why does it still pushes the zeros? Why does the program need to push a zero? Or
these are probably parameters to the next function, get message A. And function parameters can be passed by registers or by the stack.
Okay.
And the most parameters are pushed by are read from the stack. So it pushes 3 zeros because the function is popping 3 parameters. So it's pushing the parameters because it's convention by get message A to receive parameters on the stack.
Okay.
And so
and the
yeah, those
are not so important, so it's just 0 or odd.
Yeah, or default or a 0. Maybe it's adding 3 values. It's adding 3 zeros.
Okay.
But get message A is getting a message for the window. Like you press the button or you type some key, press some key, or maybe the computer wants to shut down or something. Yeah, let's get message A. Yeah, execute or step over. And it returned a 1 in EAX. The return value of get message, or one of the possible return values. Then it's ORing EAX with EAX. It's a math function, binary OR. And it does this to see if it's 0, because then comes the jump equal and it's checking the 0 flag again, maybe do the OR. Now the 0 flag got cleared, not 0, and the jump is not taken. If EAX would be 0, the jump would have been taken.
What does this mean?
A jump is control flow. It's like a call, but without the call overhead, without the instruction pointer change. It does change instruction pointer, but without stack stuff. A jump is similar to a call, but a jump is also conditional. This is a conditional jump. It jumps only if the 0 flag is set. If the 0 flag is not set, the jump is not taken.
Okay.
Yes. So jump is not taken. It will go to the layer next. Loading something from the stack into EAX. Maybe a window handle, not sure. Pushing the value on the stack. For translate message. This is also a Windows function, and it converts messages from one into another, maybe, not sure. It's doing something with a window message from the Windows system for this window. And the next is dispatch message. Then it's executing some code appropriate for the message. For example, if you close the window, it will shut down, or if you hit the button, it will execute code that got registered for the button. So step over the dispatch.
Dispatch.
Dispatch message. Step over, and you see it jumps back to the push 000. It jumps back up to E9 if you follow the arrow.
Yeah.
So what it does, it's now getting the next message. It does get message again, translate message again, dispatch messages again, and jumps way back up, and the process restarts. So this is the window main loop, and all it does is getting messages for the window and executing appropriate actions. Now, what we need, maybe you can do a few loops, maybe step over a few times again. Get message, translate message, dispatch message, and jump back top. And this would go on forever, right?
Seems like it.
Yeah, it's the main loop. And it does it so long until dispatch message will do something until EAX is 0. Then it will jump somewhere else. Maybe we can do this. Do a next loop. Stop. Again. Until the OR EAX.
Yeah.
Yeah. Step over. 0 flag is 0. Now change the 0 flag to 1.
Can I just double click here, or?
I think so.
Okay.
And now the jump is taken. You see, if get message returns a 0, it would jump, follow this jump.
It jumps over.
Yeah, and now it left the loop.
Okay. Maybe dumb question. Could that be the information I need to enter into the field to get the you did it message?
No.
Okay.
Keep following. What leave does, I have no idea. I have no idea what leave does. Go over, not important. Now it returns. And where did we come from? From there, from the main loop call. No, you remember we did call the main loop here, and now we return from the main loop. It's pushing the EIX on the stack and calls exit process, and this parameter is the return value of the program.
Okay. So this was the whole program?
Nope.
Okay.
Now comes the hard part. Somewhere in create window or something, it's registering a pointer to code which handles or dispatches the messages. And we need to find the spot where what happens when you click the button. the
Okay.
check button in the application. We need to find the code that checks this. And we can find this out by looking at the parameters. If we can find the pointer, it registers for the window to dispatch the messages. Or we can maybe peek around a bit and look if we find something by just looking at it.
Yeah.
Maybe.
Isn't it possible that when the application is open and I click the button, then isn't it possible to check in this instance what happens within the code?
We can set breakpoints. Maybe scroll a bit down if we find something interesting and put a breakpoint. We have seen this code. This is the loop, yes.
No, I mean the loop, a breakpoint within the loop somehow? Somewhere, I mean?
Yeah, you can try this out. Put a breakpoint in the loop.
Should be somewhere around here, I believe. No.
A bit up, I think.
This should be the loop, I think, yes.
Yeah.
So
maybe set a breakpoint on the push 0.
Push 0.
The 3 zeros.
Ah, there. And how do I do this? Breakpoint set?
Toggle. You can also toggle breakpoints by double click, I think.
Ah, here. Okay.
Now press run.
This run here?
We were in exit process. Relaunch the application. Run.
And now we're at a breakpoint.
Yeah, because the problem is that there are plenty of messages like mouse move, mouse pressed, key up, key down, window shown, window hidden, minimized. And the problem is if you put a breakpoint here, we will get into the debugger again. When you do the window visible, it will hit the breakpoint. This is the problem.
Okay. So I disable it.
What about compare? The compare looks interesting.
Where is it? Compare.
CMP, it's a bit down, down, down. Stop. A bit up, 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 up. With the mouse, There's a compare.
Ah, CMP. Okay, compare. Yeah.
Yeah, maybe put a breakpoint there. Or no. Then it compares some stuck memory with a value of 2.
What does the C here mean?
It's also a hex value. It's an offset to the base pointer. It's a base pointer plus 0xc. Then it will jump or will not to 1128. Jump not equal. Post quit message. Maybe do a right click there.
On the jump or the compare?
On the jump. Jump not equal. Right click. Follow in disassembler. There. It will jump there. Okay. Maybe put a breakpoint on this compare. Then remove the other breakpoint.
I already did.
Okay, perfect. Perfect. Then run. Yes. And now you should be able. Oh, you're at the breakpoint?
Yes, we are.
Step over. Scroll. Where would it lead us?
Another compare. Or what do you mean by lead us?
Oh, this looks interesting. Get message text was there. You see, this is what I mean by just looking over it a bit. Scroll down. There was some get message text, get window text A. You see the jump get window text? Yeah, put a breakpoint there. And delete the other breakpoint. And do run again. It's running now? Yes.
Seems like it.
Now enter some text. Press check. Ta-da! Now we are at a breakpoint that's more interesting. We are now at get window text A.
So this Windows text A is this one here.
This should be your text, yes.
Okay.
It's called get window text because a text field is also a window internally.
Okay.
Okay, then don't follow, step over. You see now the EAX got 4 for this call as return value. This is probably your string length.
Yeah.
And then maybe EBX. No, EBX did not change. I wonder where your text is now. Let's follow this jump. There's test. Follow this jump.
Step into.
It's only for calls. Yeah, this looks very interesting.
Here's the test, yeah.
Yeah, it's now the 40,3400 is a pointer. Moving it to ESI. Moving the 3000 to EDI. And we remember this is some memory from the application. And the 3400 is the memory address for your input in ESI, and some memory of the application is mapped to EDI.
So in this address could be the information that the program compares tests to?
Yeah, might be. We will see. Maybe put a breakpoint where we are now. And this is really the interesting spot of the app. As you said, it's comparing something with your input somewhere way below. We will see. Maybe execute this instruction.
Should I go further?
Now it's moving the next letter into the A register.
From my input?
Yes, from the ESI, it's moving a byte from the ESI to the EAX. Step over. You see, there's your T. This is hex 74, is ASCII for T.
Where's the 70? Okay, there. Yeah.
Knob does nothing. No operation. And now it's comparing 4C with the A low. It compares your letter to the letter L. Then if it's an L, it will jump If not, it will compare with an R. If it's an R, it will jump. If not, it will compare with an U. If not, it will. If
So
yes,
the
it will jump.
solution is LRUD?
Maybe, maybe not.
So when it's comparing my input with those letters, and
Yeah.
it's jumping when my letter is not L.
No, it's jumping if it's L.
Okay, if it's jumping when my letter is L, and so on, when all those letters are correct, so my letters are LRUD, then it's doing something other if it weren't this way.
Yeah, correct.
So this is the solution.
No. We will see. So it executes the instruction. It's comparing with L. If it's an L, it will jump. So if the letter is an L, it does not check RUD.
Okay, yeah.
Okay, it will not jump. Go to the next compare. Now it compares the current letter with the letter R.
Ah, okay.
Also not taken. Now it compares with U. Also not taken, not taken. And now it will jump somewhere else. Follow this.
To the beginning where we end up.
It will jump to the bad message.
Yeah.
Okay, but we got some progress. We do now know that it's only comparing to LURD.
Mm-hmm.
So maybe the solution is one of those 4 letters.
Only one of those 4.
Or we do not know what happens if the jumps are taken.
So let's try LRUD for input.
Okay, let's try this.
So run. And then we should be able to LRUD.
Don't be so rude.
L-root.
El root. It's the Spanish administrator, El root.
So
Clicking
I should
the check button.
check.
This breakpoint can be removed.
And click on run.
Yeah. And there we are.
This one. It's comparing with L.
Jump is now taken. Now it subtracts 1 from the EDI. And what's in the EDI? Maybe we should follow the EDI in dump.
So follow in dump here.
Mm-hmm. So the EDI is pointing there.
Mm-hmm.
And it subtracts 1 from EDI, means it points one address below. So the pointer will subtract it by 1. Do it. And now it's comparing the value of the new address with 1. So it's comparing the EDI with 1, or the value of EDI with 1. What is EDI now?
Don't know.
You see the EDI in the registers. Before it was 4000 and now it's 3DCF.
So I should scroll up here or what?
No. Maybe just do the compare. It comparing now the memory address with 1, and if it's greater than 1, it jumps somewhere else. The jump is taken, follow it. No. Now we're back at no. You see the green instruction pointer.
Yeah.
So it compared the EDI with 1, and if it's greater than 1, no.
But it wasn't greater than 1. It was 1. It's not greater than 1.
Yeah, it was because we were at 4330D0 in the dump. Hover your mouse over the EDI, where the EDI points.
Here?
Yeah, we did follow this in dump, and no, go with the mouse over the dump. There's a highlighted the highlighted value.
This one.
It's light gray. No, it's light gray.
Here, this one.
Yeah, this is where the EDI was pointing to, but then the 1 got subtracted. So it's not pointing there, it's pointing 1 up, one left. Hover your mouse over where the EDI is really pointing now, or you can, yeah, exactly. Or you can right click on the register, follow in dump.
Right click on the register, follow in dump.
Hover over the EDI register.
Here.
Follow in dump.
This one.
Yeah. You see now? And before we was 1 right, there was a 0, and then we subtracted 1 from the EDI, and it points now to the 2E. And 2E is greater than 1, no. So restart the application.
So click on run again.
Yeah. Yeah, you don't even need to restart. So L is not the correct first letter. Let's see what happens when we try R as first letter. Check. So your input map to ESI, the data map to EDI, comparing with L, nothing happens. Comparing with R, jump is taken.
Add EI.
So instead of subtracting 1, it's adding 1 now. Maybe now do right click on the EDI register. Follow in dump, yes.
Dump.
Now the EDI is pointing there. Then we will add 1. Where will it land?
Here.
No, this would be adding 16.
Okay, then yeah, sorry, here.
Yeah. Okay, adding 1 to EDI. Execute this. Then it's comparing the new value of the pointer with 1. Then it's comparing EDI with some constant memory address again. If if you're at this address, it will jump to congratulations. I can reveal this, but it's not taken. Then we will increment add 1 to ESI, to your input, so next letter.
Mm.
And then it jumps back to our breakpoint. And then taking the next letter.
Comparing the next letter.
Yeah, and we have no other letter.
So
0.
yeah, and then not good.
But we made some progress.
Yeah, R is correct. So those are the correct letters, but not in this particular
Order.
order. Exactly.
Yeah, maybe. You are still debugging. No, no, no. And what could we try next?
Try a different letter. So R, L, U, D, for example.
Okay, try this.
So L, increment. Now checks for the second letter. Subtract 1 from EDI.
This is right where we
One.
started, no?
Yeah.
It's as if we walked one right, one left.
Yeah. So then he jumps back to here. This is bigger than 1, so we are gonna go.
No,
back
you
to
already
the-
subtracted. You already subtracted. First we did increase the EDI, now we decrease the EDI.
Yeah.
Now increasing ESI again, next letter. And jumping to our breakpoint again.
So he's now comparing the third letter. No, the second again, and we're wrong.
Now it's subtracting 16 from EDI, comparing with 1 again, checking if it's greater than 1.
What? It's 16? Where do you got the 16 from?
Hex 10.
Ah, there.
The hex dump is 16 bytes wide for your interest. So it's like moving up.
This one here.
Not exactly. We started at the 0 in D0. 1 up, you land on 2E.
C0.
There we are now, yeah.
Yeah. Now we're back to no. But we came to the third letter. So
Yeah.
the second was correct. So it has to be RLDU. When the first two were correct, because we fulfilled the requirements of the EDI
Try it
check.
out. Yeah.
No.
Maybe put the breakpoint on the knob.
Here.
Yeah, so you see what letter you have in AL. Now it's an R. If you press run, you come directly to the next letter. Now it's an L.
D.
It's adding 16 to the EDI. It's like down.
So here, or what?
Yeah. Comparing with 1 again.
And that's not correct.
And what also is interesting, it's comparing EDI with a value. And if this value in EDI is correct, then you get the congratulations. So you can say we can control the EDI with the LRUD. And the goal is to reach the memory address of, where is it? Compare EDI. This is where we start. And your goal is somewhere else.
Yeah, somewhere where it's not 1.
You have to follow the zeros.
Yeah. So here on the fourth letter, he's adding 16.
Yeah.
So
maybe go to the compare EDI.
What did you want to say, Deja Vu?
I'm just thinking.
Say.
In the beginning, he's checking for those letters. And if one of those letters is being entered by me, it jumps to those different steps where he adds or subtracts from the EDI.
Yes.
So this means if I enter the correct letter, then he adds something and lands or ends on the specific address where it compares with 1, and if it's not 1, or so if it's greater than 1, we get the message it's not good. But it's when it's low, lesser than 1, if it's 0, lesser than 1, then it's going to be correct.
Yeah, and
so
if you look at the compare EDI, a bit up, 4 lines up.
Here?
No, 4 more.
1, 2, 3, 4.
Stop. 1 down. It compares EDI to 4032 BE. Maybe follow this in dump.
Here.
EDI. Nee. Yeah, BE was correct. Yeah. And if your EDI is pointing there, then you get congratulations. Maybe restart the application. Yeah, check. We have the R. Okay, now follow the EDI again in dump. So imagine you start there, and with an R, it's incrementing by 1. With an L, it's decrementing by 1. With an U, it's decrementing by 16. If you D, increment by 16.
And we wanted to go to this one.
Mm-hmm. Maybe don't change the dump now. Try to find this address.
PE.
32.
32 PE. Where is it? There.
BE. This is B0.
Yeah.
And E is 14. It's close to the end of the row.
Here.
Yeah, there it is. If you end up there, you won.
From am I? Damn it.
Can I ask you something, Dejavu?
Sure.
Lorud, LRUD, does it ring any bells?
RLUD.
Does it ring any bells?
And
No.
Okay.
so with R, we move one right. With L,
Yeah.
we move one left. With D, we move one down. And with U,
So,
you move one up.
right,
And
left, down, up.
yep. And if you take the challenge title into account, what do we have here?
Something with a maze.
Yes. So it basically is like a little maze where you have to move till the exit.
Did
Let's do it.
you really get how it's gonna be solved, Dejavu?
Yeah, I believe so, but it's
The memory dump screen. Can you make it a bit bigger? And then follow when you enter the first letter.
so he is comparing to the first letter.
So can you follow now? It's now to follow in dump, yes, to see how it looks like in the memory, like the EDI. Now, do you see how it looks like?
Yes.
So what should be the next letter?
An R.
Yes, and then the next correct letter, what should it be?
An U.
Yes.
D.
Wait.
And
No,
then
D,
another U.
down. No, down.
Down.
Yes.
Down. Yeah, down. Sorry.
You hit the wall.
Right. Yes.
And then the next letter?
Now I see it. So it would be right, down, right, up, right. Up, right. This way here.
Try.
Right, down, right. Let's try it this way.
checking R.
At 10. Checking next letter. It looks good.
Can I ask you for a favor?
Sure.
So can you put more letters and then show us on the different registers what you are doing? Like, for example, point out what's in EAX now, what's in EDI, like explaining what you are doing.
What each step is here doing, do you mean?
Exactly.
1 second. I just want to get to the point where he says that I'm wrong with my input.
You can call it bad boy message.
It's a technical term.
Bad boy message?
I think so. Yeah, you can say that.
Okay, now I'm here where I can enter each letter for the password. When I click on check, the program itself runs through the check routine where it compares my input with this given letters. And if the input is like those letters, it steps into the next routine where it adds or subtracts or whatever to the EDI counter. And then after the adding process or subtraction process, depends on which letter I've entered for each position in the password, it compares the EDI with 1. And when the EDI,
The value in EDI?
the value in EDI, exactly, is bigger than 1, then it jumps back to the point in the code where it says the password is wrong. And as you can see here, here's a path displayed. And each letter stands for a different way of adding or subtracting from the EDI. For example, here's 1.
I'll be right back.
Can you tell me L what it gonna do? Or like, for example, if you point down with your mouse to the memory dump with your mouse down.
When he's subtracting 1, he would go 1 to the left.
Okay,
when he's adding 16, he would step 1 down. If he's adding 1, he would step 1 right. And if he's subtracting 16, he would go 1 up. In this way, we could enter the password this way. When we start in here, we could add 1, add 16, add 16, add 1, add 1, subtract 16, and so on.
Okay.
Thank you all very much. I hope some people will learn something from this video, and we see you next time.
Thank you. See you. Bye.
Bye.
Bye-bye.